morning. I am Pranavi along with my teammate Varshini. We are here to present our project titled EV Dashboard and ADAS Warning System, which is developed as part of the Emertxe Embedded System Internship program. Our project focuses on developing a smart embedded system that combines an electric vehicle dashboard with an advanced driver assistance system. The main objective is to monitor important vehicle parameters in real time and improve driving safety by detecting obstacles and generating warning alerts. The project is built using the STM32 Blue Pill microcontroller. It receives inputs from analog sensors that stimulate the accelerator, brake, battery, state of charge, and motor temperature. Ultrasonic sensors are used to detect nearby obstacles and support ADAS features such as forward collision warning and blind spot detection. The processed data is transmitted through UART communication to a Python based dashboard where parameters such as speed, torque, battery status, remaining range, temperature, and ADAS warnings are displayed in real time. The project also includes features like regenerative braking, fault management, and an alarm system, making it a complete simulation of a modern electric vehicle monitoring and safety system. Now I will hand over the presentation to explain the project workflow and implementation in detail. Thank you.
Thank you, Pranavi. Now, I would like to explain the complete workflow and implementation of our project, EV dashboard and ADAS warning system. As Pranavi explained, our project integrates an electrical vehicle dashboard with an advanced driver assistance system to monitor vehicle performance in real time while improving driving safety. The objective of this project is not only to display vehicle parameters but also to simulate the behavior of a modern electric vehicle using embedded systems concept such as sensor interfacing, real-time processing, finite state machines, serial communication, and graphical visualization. Now, let us understand the overall system architecture. As shown in the architecture diagram, the STM32 Blue Pill microcontroller is the heart of the entire system. On the input side, the STM receives the information from both analog and digital sensors. The analog inputs includes acceleration pedal, brake pedal, battery SOC, that is state of charge, and motor temperature. These values are read using ADC module. For obstacle detection, 3HCSR04 ultrasonic sensors continuously measures the distance of nearby objects. Once all sensor data is collected, it processed by different software modules. The first module is the EV controller, which is responsible for calculating important vehicle parameters. The second module is the ADAS engine, which analyzes the obstacle distance from and identifies potential collision risks. The third module is the finite state machine, which controls the operating state of the vehicle. The fourth module is the alarm fault management system, which continuously monitors abnormal conditions and generates warning whenever required. After processing, all information is transmitted through UART communication to the Python dashboard. The dashboard displays all vehicle parameters graphically, allowing the driver to monitor the vehicle in real time. The architecture clearly separates hardware acquisition, data processing, safety analysis, and graphical visualization into independent modules, making the system more modular and easier to maintain. Now, I'll explain the complete workflow of the project. The workflow begins with sensor data acquisition. The STM32 continuously reads the acceleration pedal, brake pedal, battery level, motor temperature, and obstacle distances. These raw sensor values are first converted into meaningful engineering values. For example, the acceleration and brake potentiometers are converted them percentages, and ultrasonic echo timings are converted into distances and measured in centimeters. Once all sensor data is available, it is passed to the EV controller. The EV controller calculates various vehicle parameters including vehicle speed, motor torque, battery, state of charge, remaining driving range, motor temperature. At the same time, the obstacle distances are forwarded to the ADAS engine. The ADAS engine continuously compares the vehicle speed with the measured obstacle distance. Using these values, it calculates the time to collision, TTC, which helps determine whether the obstacle poses any danger. If TTC value becomes critically low, the system generates a forward collision warning. Similarly, if any object is detected on either side of the vehicle, the blind spot detection activates the corresponding warning indicator. Once all computations are completed, the finite state machine determines the current operating mode of the vehicle. Depending on the sensor inputs and the system conditions, the vehicle may operate in one of the following states, that is idle state or driving state or generating braking state and fault state. Finally, all updated parameters are transmitted through UART to the Python dashboard, where the driver can observe the vehicle's condition in real time. This complete process repeats continuously, allowing the system to react immediately whenever sensor value changes. Now let us look at the implementation of each module that make our project work efficiently in real time. The first and one of the most important module in our project is EV controller module. This module acts as the central processing unit for all vehicle related parameters. Its primarily responsibility is to read the sensor inputs and calculate the important parameters required for electrical vehicle operation. It continuously processes the accelerator pedal position, brake pedal position, battery SOC, and motor temperature. Based on the accelerator input, the controller calculates the motor torque required to drive the vehicle. Similarly, whenever the brake pedal is pressed, the controller activates the regenerative braking mechanism. Instead of wasting energy during braking, regenerative braking converts part of vehicle's kinetic energy back into electrical energy, which helps improve battery efficiency. The controller also estimates the remaining driving range based on the battery SOC. As the battery level decreases, the estimated driving range also decreases accordingly. Another important function of this module is speed calculation. The vehicle speed is continuously updated according to the accelerator and brake inputs, providing smooth real-time monitoring on the dashboard. Overall, the EV controller acts as a brain responsible for simulating the behavior of an electrical vehicle. The next module is analog to digital converter, commonly called as ADC module. Many physical sensors produce analog voltages. However, the STM controller processes only digital values. Therefore, the ADC converts these analog voltages into digital values that can be processed by the controller. In our project, four analog channels are used. The first channel is pedal position, and second channel reads the brake pedal position. Third channel reads used for the battery SOC charge simulation, and fourth channel monitors the motor temperature, and each potentiometer represents a real vehicle sensor. Whenever we rotate a potentiometer inside Pixim lab, the corresponding EDC value changes. These updated values are immediately processed by the EV controller and reflected on the Python dashboard. This demonstrates the real-time analog signal acquisition using the STM32 ADC peripheral. The next important module is the ultrasonic driver. To improve vehicle safety, our project uses three HCSR4 ultrasonic sensors. These sensors continuously measure the distance between vehicle and nearby obstacles. One sensor is placed at the front, and the remaining two sensors monitor at the left and right blind spots. The STM32 sends a trigger pulse to each ultrasonic sensor. The sensor emits an ultrasonic wave which reflects from nearby objects. The reflected signal returns to the sensor as an echo pulse. By measuring the echo pulse duration, the STM32 calculates the distance between the vehicle and the obstacle. These distance values are then passed to the ADC engine, ADAS engine for safety analysis. Using three sensors instead of one allows our system to monitor multiple directions simultaneously, making the simulation closer to a real advanced driver assistance system. Now let us move to the one of the most important modules in our project, ADAS engine. Here ADAS stands for Advanced Driver Assistance System. The main objective of these is to improve the driver safety by continuously analyzing the surroundings of the vehicle. The ADAS engine receives two important inputs. The first input is the current vehicle speed, and the second input is the obstacle distance measured by the ultrasonic sensors. Using these values, it calculates the time to collision, or TTC. The TTC represents the estimated time before the vehicle reaches the detected obstacle. If it continues moving at the current speed, if the speed if the TTC becomes very small, the system considers it as a dangerous situation. Accordingly, it generates different warning levels. For nearby objects directly in front of the vehicle, the system activates the forward collision warning. For vehicles detected on the left or right side, the system activates the blind spot detection warning. Depending on the severity of the situation, the warning LEDs and the buzzer are activated, and corresponding warning messages are displayed on the Python dashboard. These allows the driver to react before an accident occurs. And next, the software component is the finite state machine, also called as FSM. Instead of executing every function randomly, the FSM ensures that the vehicle operates in predefined states. Our project includes four major operating states. The first stage is the ideal state where the vehicle is stationary. The second state is the driving state where the accelerator control vehicle movement. And the third state is the regenerative braking, which is activated whenever braking occurs. The fourth state is the fault state, which is entered whenever abnormal conditions such as high motor temperature or critical warnings are detected. Using a finite state machine makes the software organized, reliable, and easier to maintain. It also simplifies future expansion of this project. And Safety is one of the major objectives of our project. Therefore, we have implemented an alarm and fault management system. This module continuously monitors critical operating conditions. Whenever an abnormal situation is detected, the corresponding warning is immediately generated. And the alarm system immediately activates warning LEDs, the buzzer, and the fault indications on the dashboard. Whenever an obstacle comes dangerously close, or the motor temperature exceeds the safe limit. The dashboard clearly displays the alarm level and the fault status, allowing the driver to understand the condition instantly. This improves overall vehicle safety and reliability. Coming to the UART communication, UART stands for Universal Asynchronous Receiver Transmitter. It provides serial communication between the STM32 microcontroller and the computer. After processing all sensor values, the STM32 sends the updated information through UART. The transmitter parameters include vehicle speed, battery SOC, motor torque, motor temperature, remaining range, acceleration position, brake position, obstacle distances, alarm status, and fault indications. This data is continuously transmitted in real time and received by the Python application. UART acts as a bridge between embedded hardware and the graphical dashboard. And finally, let us discuss about the Python dashboard. The dashboard provides a real-time graphical representation of all vehicle parameters. Instead of displaying only numerical values, it represents information through gauges, graphs, indicators, and a bird's eye view. The speedometer displays the current vehicle speed. The battery gauge shows the state of charge and estimated driving range. The EV matrices panel displays the torque, acceleration percentage, brake percentage, motor temperature, alarm status, fault status, and a communication status. The speed history graph continuously plots the variation of speed over time. The bird's eye view displays the vehicle along with surrounding obstacles detected by the ultrasonic sensors. Whenever an obstacle approaches the vehicle, the corresponding warning is immediately displayed. This graphical dashboard makes the monitoring system much easier to understand and resemble the interface used in modern electrical vehicles. Now I will demonstrate the complete working of our project in real time. Let us go with the step-by-step process, and I'll start with the step 1 by opening okay by opening STM32 cube ID. Here STM32 cube IDE is the integrated development environment used to develop and debug the firmware for our STM32 Blue Pill microcontroller. Here we can see that all the projects that were developed during the internship. Among them, I'm opening our final project EV dashboard and ADAS warning system. This project contains all source files required for complete implementation, including EV controller, ADC module, ultrasonic driver, ADAS engine, UART communication, finite state machine, alarm system, and other supporting files. And coming to the step 2, let's build the project. Now I'm building the project. Here, building means compiling all the source code together and checking whether the program contains any syntax errors or not. Here, let me take a look of it. There is no errors. The compiler successfully generated the executive binary file. As we can see, the project has been built successfully without any error. This indicates that our firmware is ready for the execution. Next, moving to the step 3, let us open Pixim Lab. And Pixim Lab is a simulation platform used in the project instead of physical hardware. It allows us to simulate the STM32 Blue Pill board along with various electronic components. Around the board, several virtual components are connected. And here we have selected the blue pill in the board, and we are in the blue pill board, and let us see the spare parts. That is our step 4. Now I briefly explain components connected to the STM32. Here we have 4 potentiometers. The first one simulates acceleration, second one simulates brake, third one simulates SOC, that is state of charts, and fourth one simulates motor temperature. And next we have 3 ultrasonic sensors, that is HCSR04. These sensors simulate obstacle detection. One sensor monitor the front side of vehicle, the remaining 2 sensors are left and right blind spots. And also we have LEDs. These LEDs indicates different warning conditions generated by the ADAS system, and a buzzer is also connected to generate audible alerts whenever a critical condition occurs. And finally, a virtual terminal is connected here. This terminal displays all UART data transmitted from STM32 microcontroller. All these components I have took from these input, output, and virtual terminals here. Here you can see input terminal, we can see the HC ultrasonic sensor and potentiometer here. And in virtual terminal I got text box to add the text, and also input output virtual terminal. And here we can see that extra one is also added, so I'll delete it. And going to the step 5, now I am opening the properties. Here we can also see we need to going to the step 5, loading the binary file. Here the binary file contains the complete firmware generated after compiling the project. Once the binary file is loaded, the STM32 starts executing the program exactly as it would be the real hardware. Now, after tapping this, we can see the changes, and we can see the output terminal, the values here. Now we can observe UART output being generated in virtual terminal. Here we can see the values such as vehicle speed, battery temperature, battery percentage, motor torque, motor temperature, driving range, accelerator percentage, brake percentage, obstacle distances, alarm level, and fault status being transmitted continuously. This confirms that the embedded firmware is running correctly. And moving to the step 6, let me open the command prompt, and you can also open this command prompt from your Windows. Search command prompt and run as administrator, you will get it. And I have already tested it. And here we can see I have tested my Python version, and I have installed libraries, and then I have went to directly to the navigation, that is step 7, to the dashboard. And here I have, you can see that the CD to the every start. Here the CD represents that the change directory. It is used to move from one folder to another folder. And here we are navigating STM32 workspace folders, then to the serial folder where the Python dashboard file is stored. And here after reaching that, we have tapped on dir, that is directory listing. It displays all file available inside the current file. Here we can see that I have stored this Python file in the serial, and it is showing here. This confirms that we are in the correct working directory. And going to the step 8, I have already done this. Going to the Python code in VS Code, I have copied the run code. We can see that in the third line, and I have copied it, and I have changed the number, that is from 3 to 1. And now when I tap on the enter button, we can directly go to the running dashboard. Here we can see the running dashboard. Going to the step 9. Now I'll demonstrate the real-time operation of dashboard by changing different sensor values in PiximLab and observe how dashboard respond instantly. These demonstrate the complete integration between embedded firmware, sensor assimilation, and UART communication. Now let us change that acceleration pedal and speed first. I'll increase the acceleration pedal with 0 speed, and here we can see that when I increase the acceleration value in PiximLab, the ADC value also increases in the output here. You can see the changes here, and the STM32 reads analog input and convert into a digital value using ADC and process it inside EV controller module. Based on the acceleration percentage, the controller inside the motor torque increases. As the acceleration percentage, the motor torque also increases. The motor torque increases, the vehicle speed also increases gradually. So now we can go to the dashboard and we can observe that here the speed has been increased from 35, I think so, and now it is increasing to the 49. Here we can also observe the torque is also increasing. This shows the real-time relationship between the accelerator input, motor torque, and the vehicle speed. And now let us test by brake potentiometer. When I increase the brake value to the high, the EV controller changes the motor operation into regenerative braking mode. During this process, the negative torque will be applied, which reduces the vehicle speed. As we can see the dashboard, the speed starts decreasing slowly and the regenerative braking operation is activated. This demonstrates the how energy recovery during braking is simulated in our electrical vehicle system. Now again, let us check the state of charge. Now I'll demonstrate the battery monitoring system. The SOC potentiometer represents the battery state of charge. Dashboard immediately displays the updated battery percentage along with the battery level. The estimated driving range is also displayed here, and next the range calculation is based on the remaining battery energy and the vehicle efficiency. This provides the driver with information about the available driving distance. And now let us go to the motor temperature. The temperature potentiometer increases beyond the safe operating level. The alarm system detects abnormal condition. The dashboard displays the increased motor temperature value. Here, if the temperature is reached a critical level, the system generates a fault indication and activates the warning mechanism. This helps protect the vehicle from overheating conditions. And also, here we can see that fault is occurred and the motor temperature has been increased. That is displaying here. And next, the forward collision warning. Now here the front ultrasonic sensor continuously measures the distance between the vehicle and the obstacle. Here I am reducing the distance of ultrasonic sensor. And here I got the alert, and the ADAS engine receives vehicle speed information and obstacle distance, and also calculate the time to collision value. When the TTC reaches a dangerous level, the system generates a warning. As we can see, the alarm status changes. The warning indication is activated, and the bird's eye view displays the nearby obstacle position. This simulates a real vehicle forward collision warning system. And now, here, let me increase it to the same position and decrease the temperature to the normal position again, so that the fault will be gone. So here we can see that the indication has been gone. And now let us test The left and right ultrasonic sensors continuous monitoring the vehicle side areas. When the object enters the blind spot region, the ADAS detects the condition, the corresponding left and right blind spot warning is activated. The dashboard bird's eye view shows the obstacle location near the vehicles. The feature helps improve driver awareness and prevents side collision. And next, as before, we have seen the fault and alarm, and also let us see the EV matrix here. We can see the EV matrix. Now coming, the panel displays the motor torque, acceleration percentage, brake percentage, motor temperature, alarm status, and fault status, and communication status. Here we can also see these values are updated continuously from STM32 controller through UART communication. This provides complete visibility of vehicle operating condition. And here we can also see the speed history. This graph stores the previous speed values and displays how vehicle speed changes over time. When I increase the acceleration, we can observe the speed increasing in graph. When brake applied, the graph shows the reduction in speed. This helps analyze vehicle performance and driving behavior. And here when let us go to the summary. Through the demonstration, we can observe the complete working of EV dashboard and ADAS warning system. The data flow is sensors in Pixim lab to the STM32 ADC and sensor processing, and to the EV controller and ADAS engine, and to UART communication, and to the Python dashboard visualization. Every module works together to provide real-time monitoring and safety features. To conclude our project successfully, demonstrate the simulation of smart electric vehicle monitoring and safety system. The project combines embedded conversion, electronic communication, real-time processing, UART communication, and Python-based visualization. The EV dashboard provides continuous monitoring of important vehicle parameters. The ADAS system improves safety by detecting the use of STM32 Blue Pill with PiximLab allowed us to develop and test the complete system in a simulator environment. Through this project, we gained practical experience in embedded system development, hardware interfacing, real-time data processing, and communication between microcontrollers and graphical applications. This project can be further extended by integrating real automotive sensors. And finally, we would like to thank Emertxe Technology, Emertxe Information Technologies for providing us these valuable internship opportunities and guidance throughout the project development. Thank you.